We have long engineered machines to follow a strict one-way protocol. A human provides an input, and the tool executes a predictable output. In this model, the human environment is treated as a fixed, unchanging baseline. Modern artificial intelligence systems update their internal logic based on the data they ingest. This creates a recursive relationship between the user and the software that traditional models of interaction are not built to capture. A paper by Podresky and colleagues IJCAI identifies this as a shift toward human-AI coevolution. Coevolution happens when the relationship between user and tool becomes recursive. Humans and AI algorithms continuously influence and alter each other's parameters in an endless feedback loop. The primary engines driving this dynamic are recommender systems and digital assistants. They permeate daily life, quietly curating the information, products, and media we consume across online platforms. While these systems influence daily choices across the digital landscape, the structural nature of this recursive interaction remains understudied in both artificial intelligence and complexity science literature. To understand why these systems frequently generate complex, unintended outcomes, we need to build a new theoretical architecture that maps this feedback loop. Treating human behavior as a static variable during AI deployment ignores the reality of how these systems function. We have to map the loop. To see exactly how this instability occurs, we can deconstruct the mechanics of a modern recommender system through a coevolutionary lens. Our baseline plots the user and recommender AI on a coordinate grid. The user's clicks generate training data. The updated AI returns the favor, shaping the user's subsequent preferences. Through this continuous, high-frequency data flow, they alter each other, causing the entire system to drift. Mathematically, these are moving targets. User preference is no longer a static data point. It is a vector constantly being rewritten by the evaluating system. By curating what the user sees, the model's output actively constrains future choices. It narrows the behavioral environment, filtering out exposure to alternative inputs. Traditional engineering relies on testing systems against fixed baseline metrics, but here, the metric itself is reacting to the test. This creates a strict systemic rule. Data generated within a coevolutionary loop can never be treated as independent or identically distributed. The AI actively alters the environment it was deployed to predict. When subjects change in response to observation, static evaluation metrics are invalidated. When the baseline environment is in constant flux, the assumptions built into standard linear machine learning methodologies begin to break down. Traditional models use this linear loss function equation, assuming the human environment stays perfectly still. It depends on this specific variable representing user input remaining independent. But when that variable expands into an active, shifting recursive loop, the linear math collapses, destabilizing the entire process. System theorists call this an endogenous change. The system is internally generating the exact forces that alter its own parameters. On a massive online platform hosting millions of active nodes, this unmeasured mathematical failure scales exponentially in real time. Because the failure is unmeasured, it leads directly to the unpredictable systemic outcomes frequently observed across society. If a recommender system detects a minor temporary user interest in sensational content, it feeds back more of that content. The user engages slightly more. The system escalates the recommendations, and a transient behavioral quirk is amplified into a systemic macro trend. Linear machine learning pipelines lack the mathematical tools required to optimize recursive socio-technical systems. To map these recursive dynamics, the researchers propose formalizing a new field of study. This discipline must operate at the strict intersection of artificial intelligence and complexity science, applying the mathematics of dynamic systems to algorithmic design. Multiplying outward, these loops form a highly interconnected human-AI ecosystem. Understanding this requires 3 levels of abstraction. The foundational scientific layer needs frameworks for nonlinear dynamics. Above sits the legal abstraction, rethinking data rights. The highest is the socio-political layer, measuring population-wide behavioral shifts. At the scientific level, researchers must construct entirely new mathematical proofs to measure and track the feedback loop mechanisms that standard models ignore. At the legal level, courts must redefine traditional concepts of user agency. Platforms are no longer neutral hosts. They are active participants shaping user decisions. At the socio-political level, governments and sociologists need these models to predict the emergence of macro-level trends, like extreme polarization and rapid information cascades. These three abstractions cannot be solved in isolation. A mathematical error in the scientific stratum scales up to create a governance crisis in the socio-political layer. Formalizing this multi-layered ecosystem is the only way to mathematically model, legally govern, and socially stabilize modern AI platforms. Accurate AI engineering is impossible if we continue to ignore coevolutionary impacts on human behavior. Recall the drifting loop between the recommender system and the user. The baseline is always moving. A complexity science framework is the only mathematical method to predict and stabilize that drift. This insight forms the foundation of the research by Pedreschi and his co-authors. Treating human choices as static baseline metrics is a critical vulnerability in current artificial intelligence development. The future of AI research must natively incorporate complexity science to properly map this feedback loop. We are no longer just building tools for humans. We are engineering interconnected ecosystems, and our mathematics must finally reflect